Hello friends, welcome to this course on radiative heat transfer. In the previous lecture, I discussed some of the methods to evaluate view factor between two surfaces bounded by vacuum. In this lecture, we will study few more methods to find out view factors between surfaces. The methods that we are going to discuss in this class are for special configurations of plates. We will discuss the inside sphere method, the unit sphere method and the Monte Carlo method. As we will see that the Monte Carlo method is generic and you can apply to any configuration, while the inside sphere method and the unit sphere method are specially designed and developed for special class of problems. So, first we will discuss the inside sphere method. Now, in this configuration we have a special case when the two surfaces can be represented as part of the same sphere. That means, we can fit these surfaces inside a sphere having some radius r. Okay. So, for example, what you see on this slide is basically two surfaces A1 and A2, okay. And these two surfaces, they are curved surfaces and they are part of the same sphere. The radius of the sphere is r and we are interested in finding the view factor between these two surfaces F12. What we will do is, we will start with small element area dA1 on surface A1 and we will take small element surface area dA2 on surface A2. The angle between the line joining dA1 and dA2 and line joining them with the center of the sphere gives you an angle of these two surfaces. Theta 1 is the angle of dA1 and theta 2 is the angle of surface dA2. Now, from just purely geometrical considerations, we can say that theta 1 and theta 2 are same, and let us say the value is equal to theta, and this angle basically is given by, it is decided by the radius r and the chord length. So, we can write down the distance between the elements dA1 and dA2, that is S, is equal to 2 r cos theta from the triangle given on this slide. So, from this triangle we can basically apply the trigonometric theorem and calculate the distance between the elements dA1. So, S is distance between dA1 and dA2, the small elements on A1 and A2. Now, we define the view factor between these two infinitesimal elements dA1 and dA2. Okay. So, we define f d1 to 2, that is the entire surface 2, which will be then integrated over the small element view factor f d1 to f d2. So, cos theta 1 cos theta 2 upon pi s square is the small element view factor between dA1 and dA2, and when we integrate over the entire surface A2, this will be the view factor f d1 to 2, and we can just substitute for theta 1 and theta 2 in this expression. So, this becomes cos square theta and we substitute for s. So, s is 2 r cos theta and this becomes now equal to 1 upon 4 pi r square. The r is independent of the integral, so it can be taken out. So, 1 upon 4 pi r square and then integrated over the surface area A2 dA2 is simply the surface area A2. So, we get basically the view factor between small element d1 dA1 to the entire surface A2 is equal to A2 upon AS, okay, where AS is the surface area of the sphere. So, this will be equal to 4 pi r square. Okay. So, we put F12, that is the total view factor from surface A1 to A2 is equal to, now we have to integrate over surface area A1. Okay. So, we write F12 is equal to 1 upon A1 as per the definition of the finite areas view factor integrated over f d1 to 2 and dA1. Okay. Now, we substitute the value of f d1 to 2 A2 by AS in this expression, and because A2 by AS does not depend on area A1, this can be taken out. So, what we are basically left with is A2 by AS. So, this gives you an idea that when two surfaces are part of the same sphere, the view factor is independent of the position of the two surfaces. So, the theta does not affect the view factor, the orientation of the two surfaces does not affect the view factor. The view factor just depends on the radius of the sphere in which we are fitting the surfaces A1 and A2 and the surface on which the radiation is basically falling, that is A2, and that is basically the definition. So, in this inside sphere method, the view factor between two surfaces does not depend on the location of either surfaces, okay, it is independent of the location. So, for this type of configuration it is very handy to calculate view factors using this simple inside sphere method. Let us see how this method can be applied to solve problems. So, we will take a problem that we have solved in the previous lecture also. We have two parallel circular discs, one disc has radius r1 and another disc has radius r2. The distance, the separation between these two discs is h, okay, and we will apply the inside sphere method to find out the view factor f122. So, this view factor we have to find out. Again to apply the method, what we have to do is we have to fit these plates inside a sphere, okay. So, let us first draw a sphere of radius r and then we will apply we will fit the plates. So, this is going to be our sphere. This is the sphere that we are going to fit our plates in. So, we have this plate A2 and we have this plate A1. This is the center of the plate, okay. So, we will just write this is the radius r of the sphere, okay, and we can just connect this also, okay. So, we will write some geometric relations and find out the view factor between these two surfaces. So, one thing before we start, you should this is the surface A1 and this is surface A2, which is not part of the sphere. We have just fitted these plates inside the sphere. So, let us write down or find out the areas. Let us call this A2 prime and this surface is basically A1 prime, okay. These are spherical caps basically, okay. So, these are part of the sphere on which we will apply the inside sphere method. We cannot apply directly the inside sphere method to these circular plates, but we can apply the inside sphere method to the spherical caps, the areas A1 prime and A2 prime. So, one thing you should just observe is that f1 to 2, that is view factor from plate 1 to 2 is basically same as f1 to 2 prime. All the radiation that basically emitted by surface 1 and falling on surface 2 will actually go to surface 2 prime also. And similarly, we can also write f21 is equal to f21 prime, okay, just by similar arguments. Now, let us start this. So, we have f1 to 2 is equal to f1 to 2 prime, okay, as already said, is equal to, now we apply the reciprocity theorem. So, we write A2 prime upon A1 times f2 prime 1, okay, just by applying reciprocity theorem, and this becomes equal to A2 prime upon A1 and then we just write f2 prime to 1 prime. Just look at this. So, 2 prime to 1 is same as 2 prime to 1 prime, okay. So, we can also write here as f2 prime to 1 is equal to f2 prime to 1 prime, okay. So, so we get this relation. Now, let us find out these areas. So, area area 1 prime. So, we need areas to calculate the view factor. So, A 1 prime is basically given by 2 pi r square 0 to let us define this angle alpha, okay, sin alpha d alpha. Let us see in the geometry what this basically represents, how are we calculating. So, we have to find out this area. So, let me just draw the spherical cap on of which we have to find out the area. We have to find out the area of this spherical cap. So, how do we calculate this? We take a annulus, this annulus we take, okay. The surface area of this annulus is 2 pi r, okay, this distance, okay, 2 pi r sin alpha, and then this distance which is basically r times d alpha, okay. So, this is going to be the area, surface area of this small annulus on the spherical cap, and when we want to integrate over the entire surface, we have to just integrate alpha from. So, this is going to be our alpha, this is going to be our alpha, okay. So, we have to integrate from 0 to alpha, okay. So, this becomes equal to 2 pi r square 1 minus cos alpha, okay, and we are using one area 1 prime. So, we will just use cos alpha 1, and similarly A 2 prime is equal to 2 pi r square 1 minus cos alpha 2. So, this is how we can calculate the two surface areas A 1 prime and A 2 prime. Now, we define the view factor f 2 prime to 1 prime as equal to A 1 prime upon surface area A s. So, this is going to be 2 pi r square 1 minus cos alpha 1, okay, and then the surface of the sphere 4 pi r square, okay. So, this basically becomes equal to 1 minus cos alpha 1 divided by 2. Now, from this equation we have view factor 1 to 2 as equal to A 2 prime upon A 1 times f 2 prime 1 prime, and this becomes equal to 2 pi r square 1 minus cos alpha 2 upon area A 1, that is the area of the disc is pi. So, we have basically we are talking about this area of this disc, okay. So, this disc has radius r 1. So, pi r 1 square. So, r 1 and r 2 are the radius of the discs, while r is the radius of the sphere. So, 2 pi r square 1 minus cos alpha 2, okay, and then we have to multiply by this f 2 prime minus f 1 prime. So, 1 minus cos alpha 1, okay, and divided by 2, okay. So, this is our area. So, we have f 1 to 2 as equal to 1 upon r 1 square. So, we can substitute for cos alpha 1 and cos alpha 2, and our relation becomes r minus under root r square minus r 1 square, okay, r square minus under root r square minus r 2 square, okay. So, this is our expression for the view factor. Now, we have to find out just the value of r, okay. So, how do we find the value of r? So, we know the separation distance between the two spheres. Let us say this was our original configuration. These are the two parallel discs separated by a distance h. The disc is having radius r 1, this disc has radius r 2. So, we have to find out the value of h, and we can write down h as equal to under root r square minus r 1 square, okay, plus under root r square minus r2 square. Okay. So, this is our the value of h. Okay. Now, we have to square this equation twice and solve for the value of r. On solving this, we get the value of r to be equal to x square minus 1 r1 r2 by h square, where x is equal to h square plus r1 square plus r2 square upon 2 r1 r2. Okay. So, this is how we can calculate the view factor using the inside sphere method. All we have done is basically fitted these two flat plates inside a sphere, calculated the radius of the sphere, and based on the formula that the view factor is equal to the area of the surface 2 divided by the area of the sphere, we have easily calculated the view factor between these two parallel discs. The next method is the unit sphere method. Again, this is a special class of method that is used to find out view factor between two surfaces. The one surface out of the two is infinitesimal, that is small area dA1 as is shown in this image, and the other surface is of finite area, the surface is A2. The surface area, the area of the surface 2 is finite, while the area of the surface 1 is infinitesimal. For this special category of problems, we can use this method of unit sphere. Now, this surface A2, we have to basically fit a hemisphere around the sphere, the surface A1, that is dA1. Okay, this sphere of radius r we have to put in, and we have to put this hemisphere in such a way that the surface dA1 is at the center of this hemisphere. Surface A2 may be inside the sphere or it may be outside the sphere, and then this surface makes a solid angle. Okay. Now, what we have to do is we have to project this surface A2 onto this sphere of radius r. So, A2 prime is basically the projected area of A2 on hemisphere of radius r. So, we have projected this surface onto the hemisphere of radius r. Now, r can be arbitrary. Okay. The choice of r is arbitrary. We will see with the help of an example. There is no restriction on the choice of r. Okay. So, we have projected surface A2 on this sphere and the A2 prime is the projected area. Now, what we do in the second step is we project this A2 prime onto the surface in the plane of the area dA1. So, this is the plane of the area. We have projected A2 prime onto this plane and the area is A2 double prime. So, this is the projected area of A2 prime on the plane containing dA1. So, we have projected A2 twice. In the first projection, we have projected it onto the sphere of hemisphere of radius r, and in the second step we have projected the projected area A2 prime onto the plane of area dA1. Okay. So, let us see how the mathematics of this method comes up. So, we are trying to find out the view factor between a small area dA1 and surface A2. So, FD1 to 2 is the view factor between dA1 and dA2, and mathematically we can define this view factor as integral over the entire surface A2 cos theta 1 cos theta 2 upon pi s square, where s is the distance between the small element area dA1 and a small element area dA2. Okay. So, now this cos theta 2 dA2 and divided by s square is basically the solid angle d omega 2. Okay. So, cos theta 2 dA2 upon s square is basically the solid angle. So, we can also write this view factor as integral over the solid angles through which surface A2 is seen by surface of infinitesimal area dA1, and we have integral cos theta 1 upon pi d omega 2. Now, d omega 2 is the solid angle, and it can also be written in terms of area of the projected surface. So, we can also write down d omega 2 is equal to dA2 prime in terms of the projected area. So, dA2 prime upon r square gives you the same solid angle which this formula gives. Okay. So, in the other sense, cos theta 2 dA2 is the projected area dA2 prime, and the distance of the original area was s, while when we are projecting it on to a hemisphere of radius r, the distance will become r. So, the d omega 2 is equal to dA2 prime by r square. So, we replace d omega 2 by dA2 prime r square in the expression for the view factor. So, f d 1 2 is equal to integration over the projection on the hemisphere cos theta 1 upon pi dA2 prime by r square. Now, the second projection area dA2 prime is related to the projected area on the units on the hemisphere by this angle cos theta 1. So, dA2 prime double prime is equal to cos theta 1 dA2 prime, okay, where theta 1 is the polar angle of surface A2 prime. So, we substitute this again. So, cos theta 1 dA2 prime becomes dA2 prime, and the denominator is pi r square, which is constant. So, this term when integrated over this area dA2 double prime just simply becomes A2 double prime upon pi r square. So, thus we see the view factor between these two surfaces, one finite and one infinitesimal, is equal to the fraction of the area of the disc. So, the disc that contains this hemisphere that contains this small infinitesimal area dA1, the disc area is pi r square, where r is the radius of the hemisphere, and A2 prime is the projected area of A2 onto this plane. So, we can say that this is a fraction of disc occupied by the double projection of A2, okay, and this is applicable to any arbitrary shape of A2, okay. It does not have to be just a plane surface, it can be an arbitrary shape. So, this method gives you a powerful way to calculate the view factor of any arbitrary shape. The only condition is that the other surface should be infinitesimal, okay, and we can measure this A2 double prime experimentally, or for some simple configuration it can be calculated using analytical formulas. So, we will see, let us see how this method can be applied to solve a simple problem. In this case, we are trying to find out the view factor between infinitesimal area dA1 located at this center of this hemisphere. Now, as we said, the radius of the hemisphere is arbitrary. So, let us see how we have chosen this radius. The surface, the second surface A2 is basically a circular disc that is having the radius a. So, this circular disc has radius a, and the separation distance is basically equal to d. Okay. So, we have to find out the view factor between these two surfaces, okay, and what we have done is we have chosen our hemisphere in such a way that the hemisphere basically passes through the edges of the disc. So, as I said, there is no condition, the disc can be inside the hemisphere or the disc can be outside the hemisphere. The radius of the hemisphere can be arbitrary. So, we have chosen to make things simple analytically in such a way that the hemisphere passes through the edges of the disc. Okay. So, as per this definition, the view factor f dA1 to A2 is simply equal to the projected area. So, we have to project this area onto the plane. Okay. So, the projected area will be equal to pi a square. Okay. So, it does not matter whether you projected it first on hemisphere or you project it on the plane. Okay. So, the projected area of the disc will be simply equal to pi a square divided by the area of the disc on which dA1 is lying, and that is basically equal to r square. So, this becomes equal to a square upon r square. Now, what is value of r? So, r from this triangle is equal to A square plus D square. So, our view factor dA1 to A2 is simply equal to A square upon A square plus D square. So, this is a view factor you can calculate very easily using this method called unit sphere method. Okay. The last in this series of view factor calculation is the method called Monte Carlo method. Now, Monte Carlo method is different from all other methods in the sense that it is basically based on statistical methodology. It requires random numbers, and the method is not just used in view factor calculation. The method is basically used in large number of problems, be it in nuclear engineering, aerospace, chemical kinetics, health physics or mathematics. So, there are large number of problems. So, any complicated mathematical or physical problem can be solved using the Monte Carlo method. All you have to do is basically define the solution domain, then randomly generate the solution, possible solutions, and then find out the exact solution using the conditions applied on the solution domain. We will understand this method with the help of a simple example, but before going to that example, let us look at the basic logic of probability and random number, because the method of Monte Carlo is based on probability theory and random number. So, probability is basically a measure of likelihood that an event will occur. So, for example, if we have a dice So, let us say we have a dice, okay, numbered from 1 to 6, it has 6 faces, and we throw this dice, okay, then the probability of getting 1 or any other number is uniform. That means the probability of getting 1 is equal to probability of getting 2 is equal to probability of getting 3. So, it is basically uniform, and this probability is 1 by 6. Okay. So, there are 6 possible outcomes, either we can have 1, 2, 3, 4, 5 or 6. So, total number of outcomes is 6, and the desired outcome either 1, 2 or 3 will be unique 1. So, the probability of getting 1 or 2 is equal to 1 by 6. So, this is how basically we define probability. In Monte Carlo methods, we use different type of probability distribution, but here I will talk about uniformly distributed random variable. So, uniformly distributed random variables is basically a special kind of probability distribution, where we say that the probability of finding a number between any two intervals is same throughout the distribution variation. So, if our distribution varies from A to B, then the probability of finding a number in this range is same as probability of finding the number in this range. Okay. So, that is basically we mean by uniformly distributed variable, as opposed to other distributions like random like Gaussian distribution and gamma distribution or Poisson distribution. Uniform distribution means that the probability of finding a number is uniform throughout the interval. So, here the interval is A and B. So, the minimum value of the random number that you will get from this is A, and the maximum value that you will get is B. So, normally in this Monte Carlo calculation we take value of A to be 0 and B to be 1. So, we are more interested in finding the random number between 0 and 1, okay, and it says that the probability of getting any number between this interval is same, that is the uniform distribution. So, let us see how this Monte Carlo method, how powerful it is and how different type of problems can be solved using this method. So, in this slide I give you a special example which is nothing to do with the radiative heat transfer or view factors. Here we are trying to find out the area of quarter circle. Okay. So, we have a circle defined in the first quadrant. The radius of the circle is 1, and we all know that the equation of circle is given by x square plus y square is equal to r square. Here in this case r is equal to 1. So, we have to find out the area. Now, suppose we do not know the area, although we know it, it is going to be pi r square by 4, but suppose we do not know it and we want to find out this area using the Monte Carlo method. So, what we will do is we will first define a bounding box. In this case we have defined a bounding box as a square passing through the edges of the quarter circle. So, we have defined this square with side is equal to r is equal to 1. The square has side equal to the radius. So, we have defined this. And why we have done it? Because we know that we are going to use uniform distribution. Okay. So, we want points to be generated using random numbers uniformly over this surface of the square. Okay. So, what we will do is we generate, let us say 100 or 1000 or maybe a million number of points. The points will be x1 and y1. Okay. Now, x and y1 represents the coordinate of the points. Okay. Now, this x1 and this y1 is basically selected from a uniformly distributed random number. So, x1 is uniformly distributed random number, it should vary from 0 to 1, anywhere it can come. Y1 is a uniformly distributed random variable, its value can be anywhere from 0 to 1, and x1 y1 is a point inside this square of radius of side r is equal to 1. Okay. And when we generate sufficient number of points, we will see that the points occupy the entire space of the square. Okay. The inside of the square entire space is occupied. So, we have to make sure that the selection process of these points is purely random. Okay. So, many computer languages come up with random number generator. So, we use this random number generator on a computer to generate random points x1 and y1. Now, we apply this condition x square plus y square should be less than equal to r square, that is all the points that lie inside the circle should be considered, and we have pointed this using red dots, and all the points that do not satisfy this condition represented by blue dots are although inside the square, but they are not inside the circle and they do not contribute to the area of the circle. So, the area of the quarter circle is then given by number of particles inside the circle, that is the red dots, divided by total number of particles that we have generated multiplied by the area of the square, which is r square or 1. Okay. So, this method very easy to implement on different type of problems, can solve complicated problems, it can give you view factors also. We will use this formula to this method to calculate view factors for complicated geometries. Okay. So, how do we calculate view factors using the Monte Carlo method? So, let us just understand the basic. Suppose we have two plates, let us call this A1 and plate 2, let us call this A2, and we want to find out the view factor f1 to 2. Okay. Now, the plates may have arbitrary geometry. In this case we have taken flat, but they can have arbitrary geometry. So, how do we solve for the view factor? So, the first point in the Monte Carlo method to calculate view factor using Monte Carlo method is to find out a point of emission. So, we randomly select a point on this surface A1. Okay. So, let us call this point as location of emission or point of emission. Okay. Now, this point of emission we will basically emit a photon, because radiative heat transfer is governed by the movement of photons. So, this point of emission basically gives you photons. Now, photons may be emitted in the entire solid angle of 2 pi. So, we have to select a arbitrary direction, a random direction using the polar angle theta and azimuthal angle psi. Okay. So, this direction of motion of this photon should be purely random. Okay. And we have to choose the polar angle and azimuthal angle randomly. Then we have to move this photon until it hits the surface A2. Okay. That is called ray tracing. So, we move the photon until it hits the surface A2 or it does not hit. Some photons may hit, some photons may not hit the surface A2. So, we count how many photons actually hit surface A2. Okay. And we also count how many photons, total number of photons we have emitted from A1. Okay. The view factor is basically defined as, so f12 is equal to photons hitting A2 divided by total emitted photons. So, in this way you can calculate the view factor very simple algebra using random numbers. The method has very high accuracy, although you have to simulate a large number of photons. As with any statistical method, the accuracy depends on the sample size. So, the sample size should be large enough if you want a good accuracy. It can be applied to any complicated geometry. As you increase the sample size, the standard deviation will also decrease. Okay. Now, how to calculate the location and direction of emission using random numbers? So, let us say we have taken 4 random numbers Rx, Ry, R theta and R psi. So, we have selected 4 random numbers. Okay. These 4 random numbers are all uniformly distributed between 0 and 1. Okay. So, let us say we have this flat surface. Okay. So, point of emission will have 2 coordinates x and y. Okay. This is the x direction. So, we write this formula x is equal to x mean, which is in this case may be 0 if we have a coordinate system located at the end of the plate. If x mean is equal to 0, our expression is simply x is equal to Rx times x max. If Rx value is 0, so the value of Rx will vary from 0 to 1, it is uniformly distributed. If value of Rx is 0, then we have x to be 0, that means the point of emission lies at the end of the plate, left end of the plate, and if Rx happens to be 1, then our point of emission will be at the other end of the plate, and this value mostly will be between 0 and 1. So, we get uniformly distribution of x coordinates, and similarly we get uniformly distribution of y coordinate. Okay. And then we get 2 more random numbers R theta and R phi. Now, we have phi as defined as azimuthal angle, and azimuthal angle as we know varies from 0 to 2 pi. So, any value between 0 to 2 pi will give you a direction of emission in the azimuthal direction. So, we define a random number or a random direction psi as 2 pi R psi. If R psi happens to be 0, then basically we are emitting the photon in x direction. If R psi happens to be 1, we are basically emitting the photon in again in x direction, because of the 2 pi angle, its complete angle is 2 pi. Now, theta angle is little tricky because of the spherical coordinate system. We basically are measuring theta with respect to normal. So, this direction has more capacity than this capacity. So, more number of photons should be emitted between normal and the direction at an angle theta, and that is why we use basically a sinusoidal distribution. So, the polar angle is basically calculated. So, it is not a uniform distribution. Photons are not emitted uniformly over the polar angle. This thing you should keep in mind because of the effect of solid angle in spherical coordinates. So, photons are not emitted uniformly over the polar angle, they follow basically a sign distribution. So, sin theta is basically under root of r theta. Okay. So, based on this relation we can calculate the polar angle, and then we can define the direction of motion n as cos psi sin theta, sin psi sin theta and cos theta. So, this is going to be our direction of emission Sij. Okay. And we can trace the photons using this vector addition, where Re is the emission location and this is basically the direction of motion. Okay. So, we can basically move the photons in this direction, and then we can see whether the photon is hitting surface 2 or not, and we can count how many photons are basically hitting the surface. Okay, thank you very much. So, here we end our study on view factors. We have discussed many methods, and some of the methods are applicable to general geometry, while some methods are developed for very specific geometries like the inside sphere method and unit sphere method. In the next lecture, we will study about radiative energy exchange between black surfaces using the view factors that we have already derived. Thank you.